Добрый вечер. Меня зовут Samaya Nissanke, and it's a great pleasure to be here to be talking to you about seeing through electromagnetic radiation and hearing through gravitational waves the violent universe, and particularly binary pairs of black holes and neutron stars that will be merging. And so before I actually begin this talk, I'd like to just mention a few things. I'm absolutely delighted to be here to talk about essentially this new field that we're witnessing that is actually just being born right now in strong field gravity astrophysics, thanks to the recent discovery of gravitational waves in the last 2 years. And so we're really seeing a new field being born, which is observationally driven. So this is really an incredible moment, and so I'm very excited to be here. And the second thing I'd like to mention is that the results that I'll be talking about are based on the work of many different groups that I'm associated with of various sizes, from thousands of people involved in the collaborations of the LIGO and the Virgo detectors, and really it's thanks to the instrumentalists and the experimentalists who have worked over decades to build these instruments that people like me are able to actually talk about the scientific results. So really to acknowledge that. And finally, just to mention that I'm also very happy to be in Moscow particularly. This is number one because this is really the home of, I think, one of the most important groups in the development of the instrumentation as well as the theory of gravitational wave detectors, Vladimir Brzezinski's group in Moscow. And so it's really a pleasure to be here. And the second thing is also for myself. I visited Moscow over 20 years ago when I was learning Russian at middle school, and it's just fantastic to be back here. This is actually where my parents met and fell in love, so it's a personal, special moment for me. And as well this week, because England is actually in the semi-final for the first time of the World Cup, so I think it's a convergence of many factors. But anyway, without further ado, I will begin. So 2 years ago, we announced the direct detection of gravitational waves and black holes for the first time. And this occurred 100 years after Einstein's theory of general relativity predicted both. And so I was really in an extremely fortunate position to be involved in these detections and these discoveries, which I'll mention. So with the two LIGO detectors, on September the 14th, 2015, we observed a pair of black holes, a 29 and a 36 solar mass black hole, essentially in spiral and merge into each other due to the emission of gravitational radiation and form a 62 solar mass black hole. Okay, and within this 0.2 seconds that we actually witnessed this merger, about 3 solar masses of energy was released during that merger. Okay, so this was the most luminous event that we've ever observed in the universe. Okay, about a billion trillion times the brightness or the luminosity of the sun, 200 billion times more luminous than the brightest supernova that we know of, and so really, and about 50 times more bright as if you sum all the light in the visible universe. So it was an extremely, extremely luminous event, and it really has transformed our entire view of sort of the violent, extremely curved space-time universe. Okay, strong field gravity. And this, of course, resulted last October in the Nobel Prize being awarded for the first detection of gravitational waves to Rainer Weiss, Barry Barish, and Kip Thorne, after sort of their decades of effort in actually building and propelling the theory as well as the experimentation of the LIGO detectors, which actually made this measurement. And since then, not only do we have this first binary black hole detection, but we also have 5 other strong detections and 1 candidate binary black hole. So we're talking about 6 events. And this is shown in this schema of a mass plot as a function of sort of the time of these events. This gives the year, the month, and the date when these measurements were made. And you can see that there's actually a variety or a diversity in the masses that are being produced to actually form these events. So they vary from the heaviest black hole that was formed, 62 solar masses from the first event. On Boxing Day of the same year, a 21 solar mass black hole was formed, as well as last June, the lightest binary black hole merger produced an 18 solar mass black hole. But what I'd like to stress is really this diversity in the fundamental properties of these black holes. Okay, so we're really uncovering a new sort of phase space of black holes of known mass. And we still don't understand what is responsible for this diversity. One of the major limitations that we face is that we actually don't know where these events happened. We don't know the precise sky position or the distance, and so we cannot answer how and why these systems or where these systems actually formed. And of course, this all changed last August, on August the 17th, 2017, when for the first time the 2 LIGO detectors in Washington State, as well as Livingston, together with the Virgo interferometer located in Pisa, Italy, the one that I'm associated with, that just happened to join the science run of these 2 detectors 17 days before, they observed what we think are 2 neutron stars colliding, emitting gravitational waves, and 1.7 seconds later, the Fermi and Integral satellites observed a burst of gamma ray emission. Okay, and so thanks to this sort of, and the ensuing electromagnetic observations that took place, we now have observed this system we call GW170817, the 17th of August, last 2017, which shown here are the masses of the system. So roughly thought to be neutron stars that merged together. We don't actually know what it formed, whether it was a neutron star or a black hole. This was not seen by the detectors. But the incredible thing was that electromagnetic emission was seen in every band of the electromagnetic spectrum for this event, post-merger, so not just gamma rays, but every part of the electromagnetic spectrum. And for the first time, we could actually precisely pinpoint which galaxy and where it happened. Again, this was an entirely sort of game changer in the field, and really, you know, I can't sort of state enough how incredibly exciting and this new era, what we call multi-messenger astronomy, is happening. The nice thing also about this plot is you can see the blue bubbles that I showed before for the binary black holes, but you can contrast them to the masses shown in purple that we inferred previously from electromagnetic observations of X-ray binaries. So these were the masses that we thought, as well as those in yellow for neutron stars from radio observations. And so you can really see that we're populating this entire phase space and having a unique probe onto other kind of systems. So it's very, very exciting being able to actually now go ahead and ask what is responsible for this diversity. And so I'll just take a step back and remind ourselves why we're so interested in black holes. And so actually Schwarzschild, 1 year after Einstein's theory of general relativity, produced the first exact solution to the Einstein field equations, which was the Schwarzschild metric, which describes a non-spinning black hole. And black holes really are sort of incredible astronomical beasts. They are the most simple and fundamental objects that we know of in the universe. They're described entirely by their mass as well as their spin. So I won't start spinning because I have a lot of equipment on me, but you get the idea. So, and that they're regions of immense space-time curvature. Okay, so they essentially have no surface. There's just an event horizon separating the interior of the black hole with the exterior universe. Okay? And so if we compress the Earth to less than 1 centimeter, it would collapse to a black hole. Okay, so just to give you an idea. Neutron stars, on the other hand, their masses vary from 1 to 3 solar masses and packed into radii of about 12 kilometers. So I was trying to ask Pavel before what was the radius of the outer ring of the Moscow metro, but I think it may be about 12 kilometers or so. Okay, so you have to imagine putting 1.5 solar masses of the sun in that area, yes, in that volume. And so the densities that we're talking about are as high as if you cram the entire of humanity into a sugar cube. Okay, so they're the most dense objects that we know of in the universe. And at their cores, they can reach a few times the nuclear density. So essentially, by smashing neutron stars together in the universe, we can use these systems as astrophysical colliders to complement ground-based instruments. So this is why, this particular event has been so exciting, also from a fundamental physics perspective. And so, of course, the game changer today is that we can detect both the gravitational waves and the electromagnetic radiation. So for this event, we essentially observed the 2 neutron stars spiraling around each other as they lose energy due to gravitational waves carrying away the energy, yes? And during their complicated merger, what we expected and what we have now actually measured is that there'll be some unbound material. This is due to the fact we have neutron stars. Okay, and this material is responsible for basically the electromagnetic emission that you're seeing from the seconds to the years timescale after the event. Okay, so we track. So really please, for the rest of the talk, when I'm talking about this binary neutron star, think we're tracking the gravitational waves for that final minute in their lifetime, and after merger, we can basically observe them at different frequencies and different time scales and really piece together what happens to the remnants and the post-merger. And so, of course, from the gravitational wave side, as I'm going to spend some time, I really would like to convey to you how we can uniquely actually measure the fundamental properties of black holes, such as their masses and their spins, as well as something about the equation of state of neutron stars. And from electromagnetic observations, not only can we actually pinpoint where the event has happened, but we can actually say something about the environment, the energetics. And so to really understand these compact object mergers, to use these in some sense as cosmic laboratories, we have to piece together both sets of information to put these systems in their astronomical context. Okay, so this is really why there's been so much excitement about this event, and why this resulted in the last 10 months of observations, making this event, I think, the most studied astronomical event that we've had so far, where 70 ground-based as well as space-based groups, over 100 instruments, actually observed this event, and as I already mentioned, detected it in every part of the electromagnetic spectrum. Okay, so it's really unprecedented. And this event was not only the first binary neutron star that was detected in gravitational waves, not only the first electromagnetic counterpart that we've seen of a gravitational wave source in every part of the electromagnetic spectrum, but it also allowed many other multiple discoveries, which I'll touch upon in the rest of the talk. Number one, it allowed us to actually, for the first time, use these systems to say something about the expansion history of the universe, use them as a sort of standard ruler. The second is that we were able to associate binary neutron star mergers with the mystery of short gamma ray bursts. For decades, we have not known what is causing these short gamma ray bursts, and for the first time, we were able to actually answer this. This event also gave us strong hints that these are the astrophysical sites of the heavy elements. So there was obviously a lot of excitement that perhaps, gold and platinum, etc., that we have on the Earth, we could explain from these neutron star binary mergers the origin, as well as allowing us to do the first tests of the speed of light and gravity with such an event. So it really was spectacular. Okay, so before going any further, I'm going to take a step back and go back 100 years or so to the theory of general relativity and Einstein's field equations, which essentially state that space-time is a dynamic entity, okay, that curves, expands, and contracts around matter and energy. Okay, and what I'd like you to take away, I'm just showing this. This is the Einstein's field equations, and this describes essentially the matter-energy density, as well as this G mu nu, really the space-time geometry, or the dynamic component. G mu nu here really encodes the geometry of this space-time. And what I'd like to stress here is that 1 year after proposing the Einstein's field equations, Einstein himself showed that if you basically take your metric that's encoding the space-time geometry and decompose it into some flat background space-time and consider just a change or a perturbation upon this metric, so we call this h mu nu, you essentially find that the Einstein's field equations reduce to describing a wave equation for this perturbation or this wiggle, this change. Yeah? And indeed, these are the gravitational waves that we've now detected. These perturbations or these ripples in the fabric of space-time that travel at the speed of light. Okay? And what he also showed, this is just a year later after he proposed general relativity, is that they're sourced by accelerating asymmetric matter sources. So what I'm showing here are in-spiraling compact binaries, but you can think of them, if you go to the gym, as basically rotating dumbbells, yes, where you need to have some kind of asymmetry to the source. And this will provide these gravitational waves. And they're essentially coherent. This is why we use this analogy to sound. They're very weakly interacting. This is both a blessing and a curse. A blessing because they basically allow information from your merger or your source to actually allow us to have this unique probe on the bulk dynamic properties of the matter, but it's a curse because it's extremely difficult to detect these waves, yes? And Einstein himself said, okay, these exist, but they'll never be detectable, okay? 100 years later, we can see actually that perhaps he was a bit pessimistic on that front. And now observable, what we're measuring, we're not measuring the intensity of light, but we're measuring, and this is why I introduced this dimensionless gravitational wave strain, this perturbation in the space-time, okay, which is time-dependent and very importantly has a 1 over distance to the source dependence. Okay, so this is why we can use these in some sense as rulers, standard rulers. It's 1 over the distance to the source. And they essentially act as tidal fields on matter. So what I'm showing here is, it does look like a kind of caterpillar or your intestine or a slinky or whatever you want to think, but is a gravitational wave propagating through a ring of freely falling test particles, okay? And basically, the gravitational wave acts as this transverse tidal field. Yeah, so you get this stretching and squeezing. And this is exactly how these interferometers on the ground, such as LIGO and Virgo, are actually measuring these gravitational waves. They're essentially measuring this tidal stretching and squeezing of the arm lengths of these interferometers as a gravitational wave passes through. Okay, so they're really measuring this tidal stretching and squeezing of the gravitational waves. So what I'm showing here are the LIGO Hanford and Livingston. These are separated by 3,000 kilometers, as well as the Virgo detector and upcoming detectors that are happening, which are important for what I'll discuss in the following. But really just to stress that we need to also have a network of detectors, not only to localize the source, but actually to make sure that these are astrophysical sources. The other thing to note is that these strains, the typical strains that we expect to detect, are about 10 to the minus 21, 10 to the minus 22. And you can show that this dimensionless wave strain is proportional to the fractional change in the distance. So if we're talking about trying to measure the change in distances over kilometers, 4-kilometer arm lengths, we're talking about delta L's, delta changes in the distance of 10 to the minus 18 meters. Okay, so that's 1,000th the size of a nucleus of an atom. So it's incredibly, I mean, therein has lied the instrumental challenge to actually try and detect gravitational waves, which has required this decades of effort. And so, just to give a schematic view, this is a very simplified picture of how these interferometers work. I will start again. Essentially, a laser beam is generated. It's split at some beam splitter into two equal and separate beams. They go to some mirror and they get bounced back and collected back at the beam splitter. Sorry, I'm going to show this again. And this happens about 200 times, this bouncing back. But essentially, the beam split and the mirrors are precisely constructed such that if there's no gravitational wave, no light is essentially collected at the detector. However, if a gravitational wave passes through, and this is really exaggerated in this movie, you can see that one arm length will essentially shrink and stretch while the other one does the opposite. And you get this interference pattern as the light recombines, and this is how you're detecting the gravitational wave. So that's to give you an idea of how these interferometers are actually working. And of course, a huge amount of the theory and understanding how to actually isolate the noise sources was really done here in Moscow. So let's go back to 2015 and the first observation of gravitational waves. So what I'm showing here is the gravitational wave strain as a function of time, so the 0.2 seconds. This event was first observed in the Livingston detector, and 7 milliseconds later, so that's the time it takes for these waves at the speed of sound to get to Washington, 3,000 kilometers away, it was seen at the LIGO Hanford detector. Okay, and so this is this wave strain that I've been talking about, and you can essentially see that it has a certain shape or certain morphology there. This is really the raw data stream. It's only been band passed and filtered. And this is the time, frequency of the power of the signal. Okay, so this, you can see this signal very clearly. It had a signal to noise ratio of about 23, shown in yellow here above the detector noise. So what I'd like to stress is just by looking at these plots, we were already able to actually extract a lot of information about the source, okay, which I think is just incredible. I mean, I think these plots really do say something about, encapsulate gravitational waves. So the first thing is, I already mentioned, please note this morphology, but also in the bottom, note how the signal ever increases in terms of frequency as well as amplitude. This is why we call this a chirp. You will hear it later on. I will play it for you. And it's really thanks to this particular morphology and signal that we can actually extract fundamental properties of the black holes and start to actually ask questions about how and where these systems, and use these for astrophysics as well as inconsistency tests of general relativity. And so as an example, if we simply just consider what we learned in high school when we talk about looking at the two-body problem, so if you simply consider invoking a Newtonian description for this pair of compact objects going around each other, if you just measure the frequency as well as the slope, the rate and change of the frequency, as well as the maximum frequency, we were able to extract not only an information about the chirp mass, which is a combination of the two masses, but we were able to say that this event had a total mass of more than 70 solar masses. But we were also able to say that it merged at at this maximum frequency, the objects were separated by 350 kilometers. Okay, so simply just from these bottom plots, we were able to say that. And so I remind you that stars have radii of millions of kilometers, the Earth, thousands of kilometers, white dwarfs, thousands of kilometers, and neutron stars, we don't believe they can be above a few solar masses. If we're talking about the total system of more than 70 solar masses, this really suggested that these were black holes. Okay, so after just seeing this within the first day, even though it came as a huge surprise, you can already extract a huge amount of information. I'll now just move on to just describe how we can actually retrieve more information about these black holes. And so for most of the other events that I've shown, these 5 other binary black hole mergers, they weren't visible by the naked eye. So you need to actually have extremely accurate models of what this gravitational wave strain actually looks like. And we call these waveforms, or you can think of them as sort of musical templates. If you want to think of gravitational waves as listening to gravitational waves, in some sense we need to have musical templates of what we expect the signals to look like to actually detect them and then extract information. Okay, so what I'm showing here is the 0.2 seconds for this first binary black hole merger, and what we have modeled this system for decades of theoretical work is that it comprised these 3 phases, the so-called in-spiral, where you have this set of well-defined orbits as the system loses gravitational waves, the merger, when the system actually merges, so you basically get these 2 black hole horizons forming one black hole. So this is really a mathematical, beautiful, I think, event. And then the final ring down, which describes the final settling of the ring down, okay? And so we call this the in-spiral merger and ring down. And this in-spiral, as I mentioned, we describe this as a chirp, okay? And it's really driven by this quantity, the chirp mass, which is this combination of the 2 masses. And the ring down is really driven by the final remnant mass and the spin. So if you can observe the in-spiral, you will learn more about the progenitors, and if your detector or the masses of your system are more sensitive to the ring down, you will learn more about the final remnant and the spin, and you can actually do sort of tests of black hole theories such as the no-hair theorem. And so, over the last decades, the in-spiral has been modeled very accurately using sort of pen and paper techniques in perturbation techniques of general relativity. So I already showed you the Einstein field equations, whereas the ring down can also be done sort of analytically, just with pen and paper. However, for the merger, we need to actually numerically solve with supercomputers Einstein's field equations, okay? Because we could no longer do these approximations that we can use here and here for these regimes actually work. And what I'll stress is that actually from this in-spiral waveform, there is even more information from just the chirp mass, but similar to sort of music, you can get actual beating of the templates of the waveforms or the wave strain, and actually pull out more information such as the reduced mass, so the mass ratio of these systems, as well as the spin orbits and the spin, so a lot of dynamics. So this in-spiral really encodes a huge wealth of information. This is why it's so powerful. And I'm just giving you an example of, I mentioned this is sort of pen and paper mathematics. This was sort of my first PhD project, just to give you an idea. So you're not supposed to be able to see all the numbers, but just to give you an idea of the kind of precision that one can actually model these waveforms. So this is a V over 7 to the C over 7, and all of these numerical coefficients here, I'd like to stress, are a prediction of general relativity, okay? So it's really just to give you a flavor of the huge complexity in terms of the machinery to model these with analytical techniques. However, for this system, the final black holes, so if you look at the velocity as a function of time and the separation, this is in Schwarzschild radii, just before they merged, were about half the speed of light. Okay, this is why it was so exciting. We've never had such an unprecedented high velocity dynamic regime to actually test and observe. We've never seen objects going at sort of half the speed of light just as they merged. And this is why we've had to actually, and there's been so much effort, and there was a breakthrough about 10 years ago in actually modeling the merger of binary black hole mergers using supercomputers. So what I'm going to show is an example from the SSX collaboration for this event, and in the bottom you'll see the gravitational waveform that is produced from the merger of this 29 and 36 solar mass black hole. In the top part of the movie, you can see essentially the so-called apparent horizons or the event horizons of the black hole, and in the bottom, essentially the extreme curvature of space-time happening. The colors show essentially the slowing down of time. So red indicates the most near the black hole throats, and the arrows are showing basically the dragging of space-time, okay? So I'll let this, and it's frozen here, just as the two black holes actually become one. And you can essentially now see the gravitational wave emission being produced from this system. So in order to actually produce this movie, about 200 CPU hours were actually used. And so you can't really actually go ahead and produce these kind of movies on the fly. It's extremely computationally expensive, and as a result, there's been a huge amount of effort to actually build in-spiral merger and ring-down waveforms that are calibrated to numerical relativity waveforms. So this is really showing a catalog of a couple of hundred of these waveforms using different mass ratios and different spins of the binary black holes, and then allowing us to really compile a catalog to then actually calibrate more analytical waveform models, yes, this in-spiral merger and ring down. And so that's been a huge amount of effort on the theory side to be able to do this. But once you have these waveforms in hand, you can actually cross-correlate, or you can compare your noisy detector output with a bank of these templates, yes, or these models, okay, and extract a whole host of information. And this is really sort of the key information that I want you to take away, that from gravitational waves you get the masses, the spins, you get some information about the distance to the source, this luminosity distance. You can get some information about where the source happened. Not very good information, but you can get some information. I'll describe this, as well as the inclination angles, so how the binary is orientated to you. And this movie really shows a schema of how one can compare the data, which is shown in blue here. This is for the first event again, against these model waveforms. So the distance first is being changed from 800 megaparsecs to 420 megaparsecs, and the total mass from 80 to 65 solar masses, which really matches the final event. So this is how we're actually doing this comparison, this cross-correlation with millions of these template banks with the data stream. Okay, so this is why we can now actually say something about the masses. So this is the lower mass and the heavier mass. No, sorry, the lighter mass and the heavier mass of these binary black holes that we've seen so far. Okay, and I'm just showing this to give you an example of the huge diversity in the masses that we're seeing of the events. Yeah, but this is really how we're extracting all this information, which is really just reliant on general relativity. Okay, there are no other model assumptions going in when we're producing this. And how well you can actually measure the particular shapes depends on which part of the waveform is most sensitive, the detector noise is most sensitive in. Yes, the detector is most sensitive in. Okay, so the chirp mass is here because we're seeing more of the in-spiral, and here we're seeing more of the final remnant for the heavier masses. Okay, so the sensitivity of the detectors is key to being sensitive to different parts of the waveform dependent on the masses of the actual system. And so we now have this challenge of how, when, and where do these binary black holes form? Because as I mentioned, we don't get very good localization. We don't know anything about the host galaxy or precisely where they actually formed. Do they come from primordial black holes, from density fluctuations in the early universe, or what we believe to be the case, but we don't know particularly the formation channel of the death of pairs of massive stars. Okay, but still it's an open question. So let's now move to last August, which was this multi-messenger discovery, and I'm going to just outline what we have learned so far from the gravitational wave side and the electromagnetic side. So shown here is the similar plot of the time frequency for this binary neutron star. Okay, what I'd like to stress is instead of the 0.2 seconds I showed before, we saw about 100 seconds of the signal. Okay, so not a fraction of a second, but about 100 seconds. This is because the system was much lower in mass, so we really saw the in-spiral. It was the loudest signal we've seen, a signal-to-noise ratio of 32, so it was extremely, extremely strong. That's why it's so visible. And it had a false alarm rate of 1 in 80,000 years. What I'd like to also mention is that it happened about 1 hour after lunch, where I very spookily actually made a scientific bet that lunchtime. I had given a talk the day before in Amsterdam at a gravitational wave workshop on multi-messenger astronomy in the 2030s. And I had started my talk saying if we want to talk about what's happening in the 2030s, we have to talk about the 2020s. And I think there will be several gravitational wave and electromagnetic events in the 2020s. And lots of people put their hands up and said, Samaya, don't you think you're being a bit too optimistic, a bit too enthusiastic? And I said, no, I'm actually going to stand by this. And the hour before, the head of the LIGO India project actually made a scientific bet saying, I don't think we'll actually see a binary neutron star before 2020. And I said, okay, I'm not a gambling kind of person, but on this occasion I thought, okay, I will actually say we will see one, but an hour later I was looking at this. Okay, so I myself was just incredibly spooked that, this was really happening. Okay, in the next, I think, few weeks, I really didn't sleep. It was probably the most exciting time. I've been thinking about binary neutron stars and their electromagnetic counterparts for about the last 12 years, every single day. So actually seeing this unfold was just, I think just a once-in-a-lifetime experience, but just fantastic. But we can compare, as I mentioned it, of course it had much lower mass than the binary black holes, but we can compare its signal length to the other binary black holes that we have seen so far. Okay, so the 8 cycles for the first event, and compare it to the, I don't think there is sound here, but maybe there is, to the minute or so that we saw in band for this event. So we were able to really do this exquisite phase tracking. And this allowed us to actually say something about the internal structure of these neutron stars. So as the orbital separation due to the emission of gravitational waves of these systems actually gets closer and closer, the internal structure of the neutron stars actually begins to play a role. So what I'm showing here in black is what I showed before for the binary black hole, this in-spiral merger ring down. And in blue here is what you expect for other objects. So just as they get to the merger, you can see this deviation in the phase. So either due to rotational deformations of the body or either to an absence of a horizon. And just before they merge, you can see tidal effects happening, okay? So essentially, basically, energy is going into these moving bulges. They're feeling each other's fields, the tidal fields of each other, of the bodies. And so it's basically speeding up the in-spiral. You're losing more energy. And of course, for this event, it would have been wonderful if we actually saw something about the merger or the post-merger, but this happened outside the frequency band of LIGO, so we were and Virgo, so we were really only able to really see something about here, but actually for the first time constrain something about the equation of state of these neutron stars, or at least put bounds. So I think that's really a phenomenal result. And just to give you an example, this is the mass of these systems, and it really happens down here compared to all the other binary black holes. Okay, but this is really sweeping out this chirp mass combination. Okay. And so, how did the electromagnetic observation of this event actually ensue? Well, gravitational wave detectors, these L-shaped interferometers, have just on their own, have extremely poor angular resolution. They're really all sky antennas, yes? So you need to have at least 3 really to triangulate the signals that are arriving to actually localize your source back on the sky. Now with 2 detectors, because there is actually a bit of amplitude information in their antenna functions, yes, you can actually localize them to these huge kind of bananas or arcs or smiles or whatever you want to think about. So for the first event, it was 590 square degrees just with the 2 LIGO detectors, yeah, and thousands for the others. I remind you that the moon is 1/4 of a square degree, okay? So we're really talking about huge swaths of the sky. So this is why we couldn't say anything really about where these events happened. But because Virgo had just come on 17 days before, we could actually localize this to 30 square degrees, this golden ring. Okay, so you can contrast that, and that is really this power of triangulation. And so we were able to actually send out the first sky map within 5 hours to our partner astronomers, which were basically, I think, every electromagnetic telescope and facility in the sky, both on ground and in space. Yeah, so we were able to send out information about the event, as well as some distance information about where it happened. It was incredibly close because it was such a strong signal. And so this movie shows how, with this information, electromagnetic partners, in particular optical telescopes, were actually able to zoom in and actually localize, pinpoint the host galaxy of this event. So this is the error of the event that was localized by just the Fermi Gamma Ray Telescope, 1,100 square degrees. If LIGO, the two LIGOs had been operating, they would have only been able to localize this event to 190 square degrees. But thanks to Virgo, we were able to do it within 30 square degrees, and in that volume, with the distance information, there were 50 galaxies. And the event happened in the third most massive, most bright galaxies. So telescopes in Chile essentially had to wait till nightfall happened. So this was about sort of 10 or 11 hours after the event, and actually most of the small aperture telescopes either went and down a galaxy list to look for the event, to see if they could actually see some kind of bright flash happening, or other bigger telescopes were able just to tile the error, tile the sky error, yes? And this really led to this amazing thing in real time happening. Within 11 hours of this merger happening, we could see this bright blue flash happen in NGC 4993 at 40 megaparsecs. It was an elliptical galaxy. Again, we saw this optical candidate that I showed you. So simply spectacular, but I'll remind you that, of course, so this is our chirp. Okay. So that's why we call it the chirp. But 2 seconds later, we had this gamma ray burst, okay? And so that really gave confidence that we were looking at a binary neutron star, yes? And the fact that we had this gamma ray burst. And what I'd like to stress is just within those first 2 seconds, without talking about anything that happened afterwards, we were able to do the first test of the speed of light and gravity and constrain this to 1 part in 10 to the 15 for the first time, just with those first 2 seconds, okay? So really incredible. Okay, and so what ensued later on for this event? I mentioned already that it was localized to this elliptical galaxy, 40 megaparsecs. And what I'm just showing here, but please don't worry because it's a very busy plot, is the timeline in different wave bands. The detections are shown in horizontal line, but this is this 1 meter 2 hemisphere group in Chile with the SWOPE telescope in Las Campanas, who identified at 10.86 hours or discovered this optical transient there in this galaxy NGC 4993. And an hour later, the Gemini telescope saw the near-infrared. The UV was seen within 15 hours by the SWIFT telescope. X-rays were seen 9 days afterwards. And the radio with the very large array was seen 16 days afterwards. Okay, so this was really incredible. I mean, I never ever myself imagined that the first gravitational wave and electromagnetic counterpart would result in basically being seen in every wave band. And this paper that I was heavily involved with and coordinating a lot of the writing involved about 3,500 authors. Okay, so it was really the largest, I guess, astronomical paper written, in the sense that I think a third of professional astronomers were involved in this campaign, just to give you an idea of the size. And so what have we actually learned? So I'm going to show this movie because I think it's good to have a bit of a pause as well. But what we predicted was that there would be two types of matter outflows. One, there would be a relativistic jet that would be thrown out after the merger, and the other that there would be this isotropic, much more spherical emission coming out from tidal tails. So we'll spend a few. So you can really see the spin spiral. It's ever increasing. This jet and this isotropic emission happening. So it's of course an artist's rendition. So, but I think it schematically shows this very nice idea of this gravitational, this in-spiral happening, and then this jet going off, and then this much more isotropic emission that was detected. And so, really incredibly, and in that movie, I hope what you were able to take away was that there are these two types of matter outflows that were predicted, and we have now actually measured. An ultra-relativistic jet moving almost at the speed of light, where c is the speed of light. And this isotropic emission, which is coming from basically tidal tails, like here, or accretion disks, winds, or basically the two neutron stars slamming into each other and creating some kind of ejector from their poles. Yes, from shock heating, okay, from these shocks. And so the principle of all this electromagnetic is that this material, these outflows, the kinetic energy, so the energy that is being carried away in their kinetic energy is basically converted into internal energy as this material expands. It cools, and then it gets reheated either by shocks, in the case of the short gamma ray burst, or by radioactivity, in the case of this more isotropic emission. Okay? And so, I mentioned that this event signified the first time that we have measured or witnessed, I guess, the astrophysical sites of what we believe are heavy elements. And these counterparts are called kilonova. These are these mini supernova-like transients. What I'm going to show you first are the observations from the ultraviolet, infrared, and optical light. These are from the European Southern Observatory's very VLT telescope in Chile over a 2-week period. And so I'm showing here essentially the spectra, the brightness as a function of wavelength of the event, 1.5 days afterwards. And so the initial shape of the spectra was very indicative, basically, of what we expect a black body or a cooling star to look like. Okay? However, as the days evolved, we saw that it became basically evolved towards redder and longer wavelengths and became dimmer. And that there were these very characteristic absorption features appearing in the spectra. Okay, and so this is important because we had never observed a transient that showed this evolution. Okay, from blue to red with this rapid decline of the blue and this slow evolution in the red spectra, as well as in the light curve. Okay, and this was very indicative of these kilonova. And they were also hypothesized by many groups to actually be spectral footprints of heavy elements. And so shown here in yellow are the elements that are now being hypothesized to be coming from these merging neutron stars in the periodic table that we all love and learned at school. And the reason why we believe that these events are responsible for creating these yellow-colored elements is that essentially the material that's thrown out is extremely neutron-rich, okay? And as basically this neutron-rich material cools, it expands, it cools, the thermodynamic conditions of about 3 billion Kelvin are such that you can actually have rapid neutron capture nucleosynthesis. You have so many neutrons there, okay? And then these create these heavy unstable elements, and these beta decay and fission back to stability, okay? So this is why you're getting this thermal source of heating, yes? This shining of this material that was detected, okay? And so this is the argument that is being used to really say that these are probably the leading contribution to producing the elements that you see in yellow here, okay, which are consistent at zeroth order to what was being predicted, which I think is just simply phenomenal. The second electromagnetic counterpart was this short gamma ray burst that I've already described, that came along actually with puzzles, and this is using the gamma, X-ray and radio emission. The first puzzle was that the X-rays and radios were detected much later than one normally sees with short gamma ray bursts. The second puzzle was this was the closest short gamma ray burst that we know with its host galaxy by a factor of 10, but it was the least energetic by a factor of 1,000 to 10,000, so we did not understand why. And the other puzzle is why were the gamma rays emitted 1.7 seconds? We still haven't answered this question. So it's exciting that, we have this association, and I think even more exciting that there are actually still open questions and puzzles left to answer, okay? But subsequent observing both in the X-ray and the radio, and literally just last week, VLBI measurements of the actual jet, of being able to actually resolve and image the jet, have been able to actually show that this event was seen about 20 degrees off axis from the jet. So we were viewing it not in the barrel of the jet, but that this jet pierced through this shocked material that I mentioned as you slam these two neutron stars. This jet pierced through, and it was this original sort of pressurized cocoon that was formed with the jet interacting through this ejector that's responsible for the fact that it was so weak in brightness, okay? So that's really now we're understanding 10 months on, actually what was the fate of the jet and the physics behind the jet. But of course, I have a 2-year-old kid, so I think I now watch a lot of cartoons, quite a bit, but we have to keep in mind, open our mind to theoretical observers. These different characters are basically different wave bands, optical, radio, etc. We really have to let the observations drive us, yes, and be very open in order for our theoretical models to explain this. And finally, I'm just going to end with the perspectives and have my own personal view on how we can actually connect our joint information to cosmology as well as to astrophysics, and what you as the public and the audience and as astronomers should be excited about in terms of what's happening in the next 5 to 10 years in this field as it expands. So I used to give this talk, or not this talk obviously because we didn't have observations, but sort of preparing the field back in 2010. I would start off actually with this analogy of this tail from the Indian subcontinent of the elephant and a blindfolded group of participants, where each participant had access to the elephant. The person at the end touches the tail, thinking it's basically a rope. This guy thinks it's a tree trunk, etc., etc. So they all have their own idea, but really in order to know that the elephant is an elephant or that the neutron star binary merger, or really understand the physics driving the neutron star binary merger, you have to actually combine all the information. So this is really, I think, where we are now. Okay, this event has happened. We've got this huge, enormous data set of observations from everywhere. And now the question is not only just interpreting it from our different angles, but really being able to combine all of this information to really understand these events in their true astronomical context. And so I already showed what we can learn from the gravitational wave side, from the wave strain, but we now have to consider what we're learning from the electromagnetic side in terms of the environment. Can we say anything about the magnetic field strength, our process nucleosynthesis, and combine it not only for the strong signal binaries, but the fact that these detectors, these gravitational wave detectors, will be switching on again next January. They've been switched off since last August. It just so happened that the science run was finishing. They're being upgraded at the moment. So this is why you haven't heard that much in terms of new events happening, but they will be switching on in January again. And they will have a considerably increased sensitivity where we have to be prepared for not just one of these events happening, but several of these events happening per year, okay, by next year, okay? So we're really talking, and by the 2020s, of tens of these events as they increase in their sensitivity, okay? So this is really where we're talking about actually looking at populations of these events happening. And then as an example of the kind of science we can do, for this first event, we were able to actually use this event as a sort of standard ruler to say something about the local expansion history of the universe. Okay, so I mentioned that by measuring the wave strain, this h of t, you have a 1 over distance to the source dependence. From the electromagnetic counterpart, you know the redshift, the host galaxy. And by combining this, you can measure parameters such as the Hubble Constant, which is basically saying something about the expansion rate of our universe. Okay? And so for this event, this is shown in blue. This is just one event. You can see that we still have quite wide error bars, sort of tens of % at 1 sigma for this measurement. And you can compare this to the green track here, which is showing the error measurements using the cosmological microwave background, and in orange using supernova 1As and local Cepheids, basically having a cosmological distance ladder. We've been able to make this measurement, and there seems to be a few sigma tension between these two results, but you can see that gravitational waves are providing an entirely independent measure. It's totally independent from both of these techniques, which is why there's been so much excitement. I've been working on standard sirens for about 10 years. I was very excited when my radio colleagues contacted me to tell me that they were able to actually image the jet and say something about the inclination angle of the binary, because this was the major limitation. One of the major limitations for this measurement was that we were not able to really measure so well the distance to the binary because it was degenerate with the inclination angle of the binary, yes? So once we knew this, so this is shown in orange here, this is just from the gravitational waves, and in purple, once you have the inclination angle from the radio, from imaging the jet, you could see that you could actually improve this original measure that I showed you in orange to this blue measure by a factor of 2 to 3, okay? And so this is really showing the power of combining gravitational wave as well as electromagnetic, in this case, radio measurements. And this is just for one event, but we looked at how many events it would take to get a precision of a couple of %. And with about 50 events, not for the radio, but for just with gravitational waves alone, we can get to a couple %. Okay, so this is really showing the power of combining the number of sources. And for the radio, if we have about 15 of these kind of events with radio and gravitational wave, we can do, with similar signal to noise ratio, we can do this kind of measurement of 1.5%. And so the challenge that we now face is we're making measurements not just of individual objects, but to actually do statistics. In the next few years, we should see, given this event, a few, perhaps, of these neutron star mergers per year. Neutron star black hole we have yet to see. This is really the next big exciting discovery. And binary black holes, several to tens per year. Okay, so this is from next year. And on the electromagnetic side, what I haven't mentioned is that there is a huge number of wide field time domain telescopes that are now essentially making multicolored movies of the universe in the optical, the radio, and the high energy side. So it's, in terms of the experiments, there's just this huge instrumental as well as software advancement that we are now seeing. Okay, so really we have to be prepared for this. And not only are we looking at having the 3 detectors I mentioned go online, but also an LIGO detector in India, as well as one in Japan by the 2020 should be coming online. So this will also help actually do the localization, pinpointing where the event happens. And in the 2030s, now in Europe, as well as in the US, there are 2 projects, the Einstein Telescope and the Cosmic Explorer, that will essentially see all the binary black hole mergers happen in the entire universe in that mass range. Okay, so we're talking about, a huge, huge number of binary black holes potentially being observed, as well as thousands of neutron star black holes. And the plans are sort of the late 2030s if these projects do get funding to go ahead. And so I think this, for me, is phenomenal. I've been telling you all about 5 or 6 binary black hole mergers and 1 binary neutron star, but just these kind of numbers to think of is quite, I think scary, but also immensely exciting. And so we should expect a diversity of the electromagnetic counterparts. This particular event, we think, formed a short-lived hypermassive neutron star, but there should be a diversity of events depending on the geometry as well as the mass ratio, as well as whether it's a neutron star black hole. So we shouldn't hold this as like our vanilla example, GW 170817. And there's a huge interpretational challenge. So many colleagues here are really working on the challenge to actually build the models or the theoretical models to really be able to do this joint gravitational wave and electromagnetic observation. Joining these observation data sets relies on modeling the binary, the merger, as well as actually the radiation transport of these events, and requires combining different microphysics as well as length and time scale. So it's a huge, huge challenge on the computational side as well. And I've been focusing on the high frequency end of the entire gravitational wave spectrum, which we have now opened up in this high frequency end with detectors such as LIGO and Virgo. But I remind you that the spectrum spans decades in frequency space, and that there are multiple experiments such as pulsar timing array, cosmic microwave background experiments, as well as future space-based missions that will be going after a diversity of different sources to the ones I've talked about. Supermassive black hole binaries, white dwarf binaries, cosmological backgrounds, and potentially, I think for me, very excitingly, are the new and unexpected sources, the things that we won't be able to actually say, oh, that was a chirp or a binary system. Yeah, I think that will be incredible as we see the totally unexpected. And so I'll just end here now with saying that the immediate future is loud and bright, and we should definitely now, I think, and sort of keep your ears open to the fact that there will be many more of these events happening, tens of binary black hole mergers per year, and the first GWEM detections happening in the next year, 2 years, as the gravitational waves improve their detector sensitivity and networks increases. But there are so many additional questions that this one event has actually brought out. Have we really found the source of heavy element formation? Do we actually know what is the engine creating the relativistic jet for these events? Can we actually say something about what was formed? Why did the gamma rays happen 1.7 seconds? What is the nature of the actual formed remnant? And so I myself am really excited to see what we'll be doing in terms of actually combining all the information and doing the joint analysis of these sources. Okay, thank you.
Oh,
thank
hello. First of all, thank you. I'm here.
Okay, thank you.
First of all, thank you for very, very interesting lecture. And in this lecture, you described the jets. And I have one more strange question about this. These jets, it's more a short time process, maybe like flash, or long time process, maybe like in quasars. How long does it exist approximately?
How long does the
jets after the Neutron Stars collapses?
Okay, so the fact that we still have radio observations of this event,
yes,
the jet is, we can still actually see this jet piercing through. Yes, but is that? I mean, we're still seeing sort of observations of this event happening, but the duration of the gamma rays just lasts a couple of seconds. Yeah, but the actual afterglow, okay, so as basically the material is basically interacting with the surrounding material.
Material and including radiation.
Yeah, that is still ongoing, yes.
Okay.
Okay, so that's why we've been able to resolve the size of the jet.
Thank you for the lecture. I have one question. Was it just a coincidence that Fermi and Integral saw the gamma ray burst? And was it important for other observations?
That's a very good question. So I think the Fermi telescope did automatically send out an alert that there was something seen, but it wouldn't have actually triggered any follow-up because it was so low luminosity that the community or GRB observers, gamma ray burst observers, thought that, it was so far away or so low luminosity that there was no point in actually doing any follow-up. Now, I was sort of on the call as soon as the email came within 15 minutes of the event to say that LIGO Hanford, one of the detectors, had actually seen an event in LIGO Livingston. Actually, there was an instrument glitch, coming back to your point about the instruments. There was a huge glitch in the noise that had to be removed, and this is why it took 5 hours to send out the sky alert. But within those 15 minutes, as soon as we knew that Fermi had also seen something, it did give incredible confidence that, this was really a real signal. Yes, this binary neutron star. And so, yes, I think that was definitely something that added to the excitement that possibly there had been a gamma ray burst with this gravitational wave signal, and the probability in terms of space and time of it happening was about 10 to the minus 8, and you can say the association. And so, yeah, I think in subsequently what happened, that was a major factor. I think, nevertheless, with just the gravitational wave signal, it was so strong, it would have still, I think the excitement would have happened in terms of the follow-up. But I think psychologically, for the community involved in observing it, yes, knowing that there was a gamma ray flash seen, and then obviously not seeing the optical or the radio or the X-ray afterglow afterwards also was like a huge puzzle that people have spent, and we have spent, months and months thinking about why.
Good evening.
Hi. Good evening.
I have two questions. The first one, how many interferometers should we have on Earth in the future to detect every collaboration of black holes or neutron stars in the universe, in every part of the universe?
So how many? So these ground-based gravitational wave detectors, because of this seismic noise limit of 10 hertz or so, are only able to detect binary black holes to sort of 100 or a couple of hundred solar masses in terms of total mass, yes? But you want to have as many gravitational wave detectors all over the world in order to actually do the follow-up, in order to localize the event, yes? So the more arrival times that you have, the longer baselines that you have, as well as if you can actually have some in the southern hemisphere, or to break this kind of degeneracy where most of these detectors all lie sort of on the same plane. Yes, so this is why there was a lot of excitement about trying to build one in India as well as previously in Australia, because you can really break sort of the degeneracy that happens because the initial LIGO Virgo detectors are there. So really as many detectors as you can have can rapidly improve the sky location. So in the case of having all 5, we can see an improvement of a factor of 5 in terms of the localization of these sources, yes? So as many as possible. But if you wanted to see kind of all, and if we build these interferometers such as the Einstein telescope, which have arm lengths of 10 kilometers, and this would be underground, so you can really try to beat the seismic limit that we have. We can potentially go down to a hertz or a few hertz, and also use cryogenic cooling, and then we're really going to see all the binary black holes, if this is your question, in that mass range, yes, of a few hundred solar masses. So that is very exciting, and also at the high frequency end, we can actually see the merger of neutron star binaries. But there's also an experiment in the US called the Cosmic Explorer, which is a 40-kilometer L-shaped interferometer, so not this triangular configuration, which is being proposed now. And the idea here is that the noise does not scale as you increase the arm length. But just imagine 40 kilometers is quite long, yes, to have these L-shaped interferometers. But the signal does, yes, because we have this fractional change in the arm length. So there's a lot of impetus to do that. But yeah, then clearly we need to also go into space to cover this part of the frequency band, and then use pulsars as clocks, extreme clocks, to try and look at 10 to the 9 solar mass, supermassive black hole mergers.
Thank you. And the next question is, these measurements of this event, can we look to relative theory from the new side, or it's only to prove this theory?
That's a really, really fantastic question, because I think it really is, as physicists, we're being faced with actually, can we only do inconsistency tests of general relativity, or can we actually say anything about other models of gravity beyond general relativity? Can we actually test, or can we say something beyond the standard model of particles from these observations? Because they're really, especially for the binary black holes, they're moving at half the speed of light. So you're really in this unprecedented regime where you're looking at dynamic space-time changing, yes? So can we say anything? And my response to you is, I think it's really only because these measurements have happened, people have realized that we are somewhat limited, that with alternative theories of gravity, we don't have predictions of what two black holes will actually look like if they're merging, or even exotic other kind of objects, not black holes. We don't actually have predictions in order to actually do these measurements so far, but there's a lot of theory, especially by young people, really exploring, opening this Pandora's box of, what are the alternative theories of gravity, and saying, okay, can we actually produce predictable waveforms that we can actually say something meaningful as opposed to just looking at deviations, yeah? And it's also the same case in terms of going beyond the standard model, in terms of saying something about whether these are quark stars or et cetera, or boson stars, and other kind of exotica. Спасибо.